Hello everyone, this is Professor Kuehn. In our last lecture, we began into Chapter 7 of A Student's Guide to the Grade Physics texts. This lecture, we will continue our discussion of Chapter 7 on beams, bones, and giants. So let me go ahead and label this. And as usual, this is from Galileo's Dialogues concerning two new sciences. And in case you've gotten a little bit lost here, the two new sciences are the strength of materials and projectile motion. And right now he is talking about the strength of materials, specifically how objects are able to or unable to support their own weight as they are scaled up in size. So let me ask a question. And this is related to Proposition 4. So this is, I'm sorry, not Proposition 4, Proposition 8 on page 93 of the text. I know the image that I'm showing on the left-hand side is from page 79. We're going to jump ahead to page 93, but I just wanted to show this diagram that Galileo has in the text while I ask this question. So here's the question. If you have a beam sticking out of a wall, so a beam projecting horizontally, as is illustrated in the diagram figure 6.6, and it is just on the verge of breaking under its own weight. Okay? So it is at the verge of breaking under its own weight. Okay, you might remember we talked about Proposition 7 in our last lecture, where we talked about how as you increase the scale of an object, the breaking moment increases more rapidly than the supporting moment, and hence at some size it will break under its own weight. So suppose this beam right here, it's projecting horizontally, it's just on the verge of breaking under its own weight. So if we were to increase the length and the width both by a factor of 10% or 5% or 1% or even 0.1%, it would collapse under its own weight. Now let's suppose you wish to make it longer. So you want to lengthen it, say by a factor of 2. You want to double the length. You could pick any number you want, but let's just say a factor of 2. Then how much thicker would you need to make it? How much thicker? How much do we have to increase the diameter? Must it be made so that it's able to still support its own weight? Right, so you've got this beam that's right on the verge of breaking. You want to make it twice as long, but it'll obviously break under its own weight then. But maybe if you just make it thick enough, then it will still be able to support its own weight. That might not be obvious to you at all that you can do that, but in fact Galileo says you can. But we're going to find that if you double the length, it's not going to be good enough just to double the width. Okay, you're going to have to change the aspect ratio. That is the ratio of length to width. So what is the answer to this question? Let me see. I think, why don't we do this by way of an example? So let's work through, instead of just providing the answer straight away, let's work through an example of a limestone pillar. Oops, my tablet is freezing up. We'll have to wait a moment. Of a limestone pillar. And we'll do this in a geometrical way like we have been doing so far. So let me go ahead and jump ahead to the section of the text. This is chapter 6. Now we're beginning into chapter 7 on beams, bones, and giants. And we are going to be looking at Proposition 8, which begins on this page, page 93 at the bottom. Given a cylinder or prism of the greatest length consistent with its not breaking under its own weight, and having a given greater length, to find the diameter of another cylinder or prism of this greater length, which shall be the only and largest one capable of withstanding its own weight. Okay? So what he's going to, this is his proof over these 3 pages. It's sort of a long proof, and I will go through this and then we'll come back to this diagram later. So let me drag this over here so I have a little bit more space on my sketchbook. And hopefully this will be enough room. Okay. I kind of drew that in the middle. I might have to go to the right and then come back to the left. I hope that's not going to be too confusing. Okay, so let me draw a couple of pictures. So here's a wall, and here is one pillar sticking out of a wall. Okay, so here's the wall right here. And let's make this pillar have a diameter. This will be pillar A, which has a diameter dA and a length LA, and this is its center of gravity, and it's got a weight W sub A, and it's got a longitudinal resistance R sub A. Okay, and then we've got another limestone pillar sticking out of a wall. And we will call this one pillar B. So this has a diameter D sub B, it's got a length L sub B, it's got a weight W sub B, and it's got a longitudinal resistance R sub B. Okay, and this one, they are both on the verge of breaking. Okay, breaking. So what do we mean when we say that these are on the verge of breaking? Okay, so if this one's on the verge of breaking, we're saying that the same material, they're both limestone. This one's on the verge of breaking. This one's longer, and it's going to potentially have a different diameter. And we're going to figure out if it's longer, if this length has some relationship to the this length, what is going to be the relationship between the diameter of this one and the diameter of this one, so that this one also is just on the verge of breaking. So what do we mean when we say it's on the verge of breaking? We mean, once again, that the supporting moment is exactly equal to the breaking moment. So I'm going to draw the fulcra here. And let's do the one on the left first, the beam A. Well, the supporting moment has to be exactly equal to the breaking moment. And likewise over here, for this one, the supporting moment has to be just equal to the breaking moment, right? What is the supporting moment of this one? Well, it's just the longitudinal resistance RA times the diameter of A over 2. Remember, as always, this is the lever arm for the supporting moment, and this is the supporting arm for the lever arm for the supporting moment of beam B. Okay, and what about the breaking moment over here? Well, that's just the weight of beam A times the lever arm, the distance that is from the fulcrum, so that is LA over 2. And let's do that for this beam over here. Let me go ahead and draw a line, a dashed line vertically here, so it cleans up my formulas a little bit. Okay, so this one, the supporting moment is RB times the diameter of B over 2, and this one has weight B times the length of B over 2, right? So this is the condition that this one's on the verge of breaking and the condition that this one's on the verge of breaking. Now what we want to do, our goal, is to find the ratio of the diameter of B to the diameter of A. That is, how much thicker does this have to be than this when the length is made longer than this length? Okay, so let's go ahead and find dB over dA. Well, we have an expression for dB right here. We can just rearrange this formula and solve for dB and put it in the numerator. So let's cancel out these 2's. dB is going to be equal to the weight of B times the length of B and divided by the longitudinal resistance of B, right? And what about dA? Well, we've got this right here. Let's cancel out the 2's. We'll move the RA to the denominator, and likewise we have the weight of A times the length of A divided by the longitudinal resistance of A. Okay? Now, this looks like this just goes, the ratio of the diameters goes as the ratio of the lengths. That would be your first impression. But as before, we have to think a little bit more carefully about this because the weights are implicitly dependent upon the diameter and the length. As you increase the diameter or the length, you're also increasing the weights. And likewise, the longitudinal resistances are dependent upon the cross-sectional areas, which are in turn dependent upon the diameters. So we're going to have to make explicit those hidden dependencies here. So how do the ratio of the weights, so we'll call it, let me do this like this, the weight of B compared to the weight of A, this ratio here is related to the volume of B compared to the volume of A. And the volume of B is going to go as the diameter of B squared times the length of B. And the weight of A is going to go as the diameter of A squared times the length of A. So this right here, let me even color code this. So this is the ratio, that's not a very good different color, let's do green. This right here is the same as this ratio right here. Okay? And now we've still got the ratio of the lengths, length of B over length of A. That's the same as this. And then we've got here an RB in the denominator and RA in the numerator. Let's just take another step and do that right here, RA over RB. Okay, let's combine these right here and find out what the ratio of these resistances are. So dB squared, my tablet froze once again, dB squared over dA squared times LB squared over LA squared. And now the ratio of these resistances here, let's make these flesh colored like that. And that is going to be, well, remember the longitudinal resistances go as the cross-sectional areas. And so we can write RA over RB as the diameter of A squared over the diameter of B squared. We've got A in the numerator, B in the denominator. Oops, I guess I should have made that flesh colored. I'll go over it like this. So that's that. Okay, now notice what's going to happen. There's a simplification here. This cancels with this, and this cancels with this. And so we're left with dB over dA is equal to LB over LA squared. Okay, now what is the point here? What have we done? We basically said if we have one pillar that has a particular diameter and a particular length made of limestone sticking out of a wall, and it's just on the verge of breaking under its own weight, and we want to make another limestone pillar sticking out of the wall that has a different length, a longer length, so length B is bigger than length A, and this one we want to be just on the verge of breaking under its own weight. What do we have to do to the diameter so that it can just support its own weight? And this tells us that the diameter, you have to increase it as the square of the length. That is, if LB over LA is 2 to 1, so this one is twice as long as this one, then you have to make the diameters 2 to 1, 2 squared is 4 times the diameter. So if B is 2 times as long, then B must be 4 times as thick in order to support its own weight. That is the point that Galileo is making. You can scale something up, but you have to have a different aspect ratio. It has to have a different diameter to length ratio. So it will have to be deformed, so to speak. Okay? And this is precisely the point that he is making in this diagram. And so let me just read this paragraph right here to you, and I think that'll be a nice summary of what Galileo is getting at. So let me put this over here just to get a sense of where we've been, and then I'll read this paragraph and then we'll be done. Okay, so he says, from what has already been demonstrated, you can plainly see the impossibility of increasing the size of structures to vast dimensions, either in art, that's human-made things, or in nature. Likewise, the impossibility of building ships, palaces, or temples of enormous size in such a way that their oars, yards, beams, iron bolts, and in short, all their other parts will hold together. Nor can nature produce trees of extraordinary size because the branches would break down under their own weight. So also, it would be impossible to build up the bony structures of men, horses, or other animals so as to hold together and perform their normal functions if these animals were to be increased enormously in height. For this increase in height can be accomplished only by employing a material which is harder and stronger than usual, or by enlarging the sizes of the bones, thus changing their shape, until the form and appearance of the animal suggests a monstrosity. This is perhaps what our wise poet had in mind when he says in describing a huge giant, impossible it is to reckon his height, so beyond measure is his size. And this is from one of Ariosto's poems. And then he goes on to say, to illustrate briefly, I've sketched a bone whose natural length has been increased 3 times, and whose thickness has been multiplied until, for a correspondingly large animal, it would perform the same function which the small bone performs for its small animal. So this is showing exactly what we talked about in this formula. If you make it twice as long, you're going to have to make it 4 times as thick in order to perform the same function. This is a very important result that Galileo arrives at, and there have been a lot of people who have followed in Galileo's footsteps in using this kind of technique to understand the viability of living organisms and built structures. And I will stop there.